So, welcome everybody for this last series of lecture. So, we will start with today with a talk by Thierry Bodineau. So let me just say a few words about our speaker. So Thierry got his PhD in 1997 in Paris 7. Under the direction of Francis Gomez. He then joined CNRS. He stayed at Paris 7 for a while before moving to École Normale Supérieure, Rue d'Ulm, and then to the École Polytechnique. He has been working in equilibrium and non-equilibrium statistical mechanics since his early days. And about 8 years ago, he started a long-term project around a famous paper by Oscar Langford on the emergence of the Boltzmann equation in the dynamics of hard sphere gas. So this is a project that he has been working on with Isabelle Gallagher and Laure Saint-Raymond for many years. And today he's going to tell us about the last results in this program. So, and before we start, I also have to handle him the medal
Thank you very much.
to remember him of this day. Okay, so.
Thank you very much for this introduction. So today I'm going to report on some work I did over the past few years in collaboration with Isabelle Gallagher, Laure Saint-Raymond, and Sergio Simonella. What we are going to study is the dynamics of hard sphere gas in a kinetic limit. And in this limit, it's known that the Boltzmann equation is a good approximation of the distribution of the gas. And however, Boltzmann equation doesn't share all the properties of the microscopic dynamics because it is a dissipative equation, it is irreversible, unlike the microscopic system which follows Hamiltonian dynamics according to a basic law of physics. So the question we would like to address today is how good is a Boltzmann equation and what are the corrections to Boltzmann equation. And for this, we are going to look at the finer scale of this microscopic dynamics. And along the way, this is going to shed some light on the emergence of irreversibility in the kinetic limit and on the specific role played by the microscopic dynamical correlations. Okay, but let me first proceed slowly. And in the first part of the talk, I'm going to review what is this microscopic dynamics I want to present and recall the convergence of this microscopic dynamics to the Boltzmann equation, at least in short time. And in the second part of the talk, namely the blue items on the slides, I will explain a new feature, the fluctuation around Boltzmann equation, the role of the cumulants, which is derived through cluster expansion, and ultimately the large deviation of the hard sphere gas. So let's start with the basic model. We consider a system, let's say the unit cube 0, 1 in dimension d. D will be larger or equal to 2. And in this system, we will consider immense or huge billiard with plenty of balls, the hard sphere. They move along in a straight line, and when two spheres touch, they simply bounce against each other. It's elastic collision, and this is going to be our dynamics. To make things simple, let's say that our domain is periodic. So, the microscopic system will be encoded, therefore, by a huge collection of coordinates, so, which I'm going to call Zn throughout the talk. At time t, Zn is the position xi of particles and the velocity of these particles, vi. So what are the important features? So this dynamic is actually extremely unstable, but what we're going to do is look at the large n regime. So when the number of particles goes to infinity. So of course, since the box will remain finite, one has to scale down the size of these balls in order so that they all fit in. And actually, we are going to use at a very specific scaling known as the Boltzmann Grid scaling. So the number of the balls n is going to be scaled with epsilon. Epsilon is the diameter, such that n times epsilon d minus 1 is equal to 1 at any time. So the kinetic limit will always be n goes to infinity, epsilon goes to 0, and they both go together to the limit while they satisfy this constraint n times epsilon d minus 1 equal to 1. So that's what we're going to do. Of course, if you haven't seen it at the first time, it might look a bit strange, this Boltzmann Grid scaling. So what is the reason? The reason is simple. We would like to have a mean-free path of order 1. So mean-free path means that if you take a typical particle, it's going to travel for a length of order 1 before having a collision with another particle. So if you take a typical particle and let's say it's going to span a tube, and a tube of length 1, and since the particle has a diameter epsilon, the volume of this tube will be of order epsilon d minus 1. So it's a tiny tube, and in this tube, we don't want too many particles, otherwise there would be too many collisions. So we want typically of order 1 particle in this tube. So if we imagine that all the other particles are uniformly distributed, what does it mean? Well, it means that n times the volume of the tube should be equal to 1, roughly. So that's the reason of the Boltzmann Grid scaling. We don't want too many collisions. Let's say, on average, 1 collision per unit time. Okay. Let me emphasize that in this limit, epsilon goes to 0, the gas, with this scaling, the gas will be extremely diluted. Okay? So it's really a dilute gas. The dynamics is completely deterministic. So it's a billiard. Or this is, of course, maybe a fancy way to rewrite the billiard, but basically particles are going in straight line. And what is important is that the collisions are elastic, namely when two particles collide, their momentum is conserved. So when two particles collide, the velocity vi, vj are changed to vi prime, vj prime, but the momentum is conserved, the energy is conserved. So this is the microscopic dynamics, and n is large. There's no randomness at this stage. Let me emphasize two important points. The first one is that the dynamics, the microscopic dynamics, is reversible. What does it mean? It means that if you take two balls, for example, and they move along, they're going to collide. and bump against each other, if at a certain time you inverse the velocities, they will come back exactly to the same position, okay? So you can always, at any time, you can always reverse the velocity and get back to the initial position. However, the very important point of this dynamic is that there are huge dynamical instabilities. What does it mean? It means that my tiny balls here of diameter epsilon, so epsilon is minute, if I shift one by just epsilon, instead of colliding, they're going to miss each other. And the whole history will be different. So a little shift of the dynamic might lead to very different trajectories. And of course, we have n particles, so there's potentially a lot of things which can happen along these dynamics. Last feature I want to stress is that we will not follow exactly the position of every single particle. What we're interested in is to have a statistical description. So even though the dynamic is deterministic, we'll have some source of randomness initially because all the particles we start according to some initial distribution, and this distribution evolves following Liouville equation. So in this case, Liouville equation doesn't look that scary. It's just a transport equation. Particles move in straight line. Of course, there is a twist because the domain is extremely complicated. Each time two particles touch each other, there's specular reflection, and that's what makes things complicated. Okay, so far I told you about the microscopic dynamics, and now what we have to do is make it a bit precise what kind of initial condition we're going to consider. We're going to consider actually, the simplest thing you can imagine, namely, let's say that particles initially are independent. So each particle will have some distribution, F0. F0 is a distribution on the position and on the velocities, and we consider the product. So product doesn't work exactly because, of course, we have this exclusion condition. Particles are not allowed to overlap, and we just, bias slightly this initial distribution with the exclusion condition. However, we're going to look at some dilute gas, so let's say that the measure will be essentially product. Okay, there's some correction, but a priori not that important. Okay, to make things simpler, I've always started assuming that n, the number of particles, was fixed. It's a bit more convenient to take it random and to consider a grand canonical formalism. So in the following, for us, the relevant parameter will be the mean of n, the expectation of n, and I'm going to call it nu of epsilon. Again, what is important is that this expectation follows or is linked to the size of the particle according to Boltzmann Grid scaling. Okay, so we have some initial distribution. We have the dynamics of n particles, but actually we don't really care about all this structure, this microscopic structure. The natural thing is to do some kind of projection and look at the typical density of one particle at time t. And this I'm going to denote throughout the talk by F1 epsilon. Okay, so F1 epsilon t, which, it's here, is just the probability that a typical particle, or the like, say particle 1, is at the position or has coordinate z1 at time t. And the question we are asking for is how does this converge, or where does this converge in the Boltzmann Grid scaling when the number of particles goes to infinity. I need also another notation, and because it will be relevant also for us, is to look not only at one typical particle, but at the distribution of k typical particle, and this will be denoted by Fk. Okay. So let's try to understand, at least heuristically, how this typical distribution is going to evolve. Well, your particle moves first in straight line, and therefore we expect that it follows some basic transport equation. However, at some point it may collide, and then we have a second term which is going to record, let's say, the collision between the particle 1 and the particle 2. So if you haven't seen for those who haven't seen the collision operator before, it looks a little bit daunting, but it's actually, I mean, simple to understand. You have particle 1, which is at position x1. You have another particle at position x2, which is exactly the center, has to be at distance epsilon, so in the direction nu of x1. So the two particles collide, and the nu is the angle between these two particles. And before the collision, you have certain velocity. After collision, you have other velocities related by the angle of collision. So, of course, this cannot be determined straight from the position of the first particle, because you have to know what is the distribution between the probability of having particle 1 at this position and particle 2 just next to it with the different velocities. But essentially, I mean, this operator takes into account the probability that the two particles are next to each other with a certain angle and leads to some deflection. Just a few words. This collision is extremely singular because it happens on the surface, so on some object which is of area epsilon d minus 1. So it's really tiny. However, when I say particle 1 bumps into particle 2, it's not exactly correct. Could have touched any of the other n-1 particle, and therefore there's this delicate compensation between n and the epsilon d-1, which ultimately gives you this equation, where you have the first marginal, or the typical distribution of one particle evolves, but it depends on the distribution of two particles. So at this stage, the simplest thing one can do to close the equation is to rely on the so-called microscopic chaos assumption. Namely, the gas is extremely dilute, therefore particles were independent initially, therefore they should be relatively independent at a certain time, and the position of, or the joint position of the two particles should be roughly given by the distribution of the product, as if both particles were independent. So this microscopic chaos assumption is a bit delicate, and I'm going to discuss it later on. But at least if you assume it, you end up with what we were looking for, namely Boltzmann equation. So that's what I've just told you is basic derivation of Boltzmann equation you can find in textbooks. And what is, of course, interesting in the Boltzmann equation, so now in the limit, when epsilon goes to 0, both position of particle x1 and x1 plus epsilon coincide. Therefore, in the Boltzmann equation, you have only one type of density, but the position is the same. An interesting feature, because I mentioned some stochastic structure of the Boltzmann equation, is that the collision, or the angle at which particles were in the microscopic system becomes random, and therefore it's like the Boltzmann equation is basically boils down to choose randomly some angle nu, to choose randomly some velocity v2, and observe some collision. Okay, so the question will be how can we justify these heuristics? this equation was stated by Boltzmann a long time ago, more or less along these heuristics, and very early there has been an objection about it, and in particular the reversibility of the microscopic structure I mentioned earlier doesn't hold at the level of Boltzmann equation. As I said before, Boltzmann equation has really intrinsically a stochastic flavor. And this stochastic flavor comes from two facts, actually. Initially, we start from some random initial data, and even so, the measure itself, the evolution itself, is completely deterministic. It is extremely unstable, and these instabilities generate somehow the stochastic structure along the flow. And we would like to understand a bit better this convergence and see how this somehow two different structure, deterministic or limiting stochastic structure, reconcile. Just one side remark, and I won't go into that, but it's completely different, for example, from mean field models. Vlasov equation, the limiting equation, doesn't behave at all in the same way. In a sense, it is much closer to a stochastic microscopic model. And Mark Kax understood that long time ago, and he proposed a microscopic stochastic process which is going to have the homogeneous Boltzmann equation as a limit. So it has no spatial structure, it's a mean field-like process, but since it's stochastic, it reproduces the Boltzmann equation in the limit. So I won't use this process, but I just want to give you a rough idea of how it goes. There is no spatial structure, so basically one just has a collection of velocities, v1, v2, vn, n velocities. And the process goes as follows. Choose a random time. At a random time, choose two particles randomly, let's say Vi, Vj. Then choose a random scattering and change their velocity to Vi prime, Vj prime. And there's absolutely no spatial structure there, but ultimately one can recover the homogeneous Boltzmann equation. So what I want to explore now, when we're going to look at the finer scale beyond Boltzmann equation, is how close this stochastic description is from the deterministic dynamics of hard sphere. So the Kax model will serve as a guideline somehow. But before doing that, let's go back to our actual problem, which is, can we justify the molecular chaos assumption? Namely, can we justify this factorization and prove that at time t, the typical density of two particles is given by the product of the single density. This is often called propagation of chaos, but what I want to stress is that this notion of propagation of chaos, to be relevant, it has to be valid on an extremely singular set. It's not like any position or any type of coordinates. You want the factorization for particles which are colliding. They're next to each other. They are at a distance, say, almost zero, and they're just about to collide. And you want this factorization on this singular set. So how does it go? Let's look now at the system of particles, the full system, and look specifically at two particles on this picture. Here is x1, here is x2. and they're moving in the direction V1 and V2. And I would like to prove the factorization. But they're in very specific position because they're just about to collide, okay? And I want to say that essentially they haven't met each other in the past. They have very little correlation, and therefore the measure should be independent. So it's a tiny set. They're just about to collide. We have these two tubes of width, epsilon, but okay, still we expect the factorization. Well, on the other hand, there should be memory effect because we know the dynamics is reversible. So if I choose the same two particles, but with slightly different velocities, now V1 and V2 are going far, seem to go apart, but actually if I go backward, if I trace their dynamics backward, the tubes I mentioned earlier, they are overlapping. Namely, this particle must have touched each other. There, I'm not expecting factorization. It's not possible. Some memory effect has been built along the dynamics. So these type of events have to neglect and prove that they are extremely small. And actually, I mean, they are small because if you look at it, it means that the tube, if in the backward dynamics, the tube formed by the particles, they are tiny. They are of width epsilon, area epsilon d minus 1. So this event is minute. However, as I said before, these events we want to neglect of the two tubes which are intersecting in the backward dynamics. They have exactly the same size, geometrically at least, as the events we want to capture, which are those where the two tubes are going to meet in the forward direction. So, okay, in both cases it's tiny, and we have to understand something there. Let me briefly, for the statements, because I still haven't told you about the convergence to the Boltzmann equation, let me try to formalize these bad sets where you have two particles with position and velocity such that in the near future they're going to meet if you follow the backward direction. And I'm going to call this set bad. And for two particles, it's going to be B of 2. And for K particle, if I have K particles, it's going to be B of K. Okay, it's just the exact formula is not that useful. And let me explain, or let me phrase, what is the convergence theorem to Boltzmann equation. I will quote after the long list of people who have been working on that. But to summarize, let's start with normal product distribution with particle distributed according to initial distribution F0 times maybe the exclusion, say, but it's essentially product. Assume that F0 is smooth enough. Then what the theorem says is that there is some positive time, T star, such that the typical density of one particle converges to the solution of Boltzmann equation, small f, which is written below. And this convergence holds in the Boltzmann Grid limit as before. This convergence can even be quantified in terms of some term vanishing when epsilon goes to 0. Actually, one can go one step further, and one can prove this propagation of chaos I was mentioning before in a relatively quantitative way. If I choose now at the typical distribution of K particles, well, this is going to converge to the product of the distribution, provided we're not considering this particle in the bad sets I mentioned earlier, the ones we want to disregard. So there's, I mean, the convergence, it's not like a full convergence. It's relatively precise, but there's some sets which we simply have to neglect. So this theorem, often referred as Lanford theorem, because it has been first proved by Lanford, has been greatly generalized over many years. So here is a long list of contribution, but it's by no means complete. I just want to emphasize one series of very important contributions we've been using is work by Gallagher, Saint-Raymond, Texier, and Pulvirenti, Safirio, Simonella, and Denlinger, and again Pulvirenti, Simonella, where the first very quantitative type of convergence were established for the convergence to Boltzmann equation. In summary, what do we have to keep in mind? Two facts. First, the convergence is on a short time, and in this talk I will not mention a longer time of convergence, and actually it's an open problem in this general setting. Second thing is that the convergence is only valid for a huge, actually, class of coordinates, but with the exception of some bad configuration, which are neglected. And that's, on this specific configuration, that's where the irreversibility emerges, actually. By neglecting certain things, we are actually losing some memory in the system, and therefore we recover some equation as Boltzmann equation, which is dissipative, and in particular, so what we are forgetting are these so-called recollisions. Okay, so this is more or less for state of the art in terms of what. And now I would like to go and explain what we did more recently. To do that, I want to rephrase slightly the statement of the convergence to Boltzmann equation, not in terms of the typical density of a particle, but in terms of the empirical measure. So empirical measure, I just choose a test function, let's say h, depending on position, velocity, average this test function over n, and look at the difference between this test function against Boltzmann equation. So here, I just want to assume that n is constant to do a simple computation. So, of course, I expect that this square goes to 0, and I can check it easily because I expand the square, and I have two terms. First term is when I repeat the same particle in the expansion. So that goes like 1 over n. Second term is the cross product, the correlation in the system. So the first term goes to 0 because there is a factor n divided by n squared. And the second term, well, the cross product, they are, I mean, of order 1 terms, the compensation is of order 1. But the correlation we understood from the theorem mentioned earlier, that this is related to the 2-point correlation in the system, the 2-point correlation factorized by the chaos property, and therefore the second term goes to 0. Okay, so this is another way to view Boltzmann equation, just the mean converges to the solution, or the empirical measure concentrate to the solution of Boltzmann equation. Well, let's say that now we've been able to look at the law of large number. The next step is to look at the central limit theorem. So instead of dividing by n, I'm going to divide by square root of n, and I do the same trick. I expand, and what do I see? Well, what I see is that the first term now doesn't vanish, both n compensate, and the second term is a bit more tricky because now I have n squared cross terms, and I have I divide only by n, and therefore the correlation have to be analyzed in a much better way. And so that was already understood a long time ago by Herbert Spohn, that if one wants to look at the fluctuation, now the correlation matter. I can't just say the recollision vanish and this doesn't matter. No, now we have to look more carefully at the system. So that's in this direction I want to proceed now for the rest of the talk. Okay, by the way, n was fixed, so to make computation easier, I'm going to look at the grand canonical formalism. So you should think, instead of the n, you should think now of mu. mu is the mean, divide by square root of mu, but essentially it's the same. So what is our next goal is to understand the correction to Boltzmann equation. So we just look at the empirical measures, subtract the mean, and we get the so-called fluctuation field. So it's very rough, and we want to understand now the time evolution of these fluctuations. So the theorem is the following, so obtained jointly with Isabelle Gallagher, Laure Saint-Raymond, and Simonella. Same assumption as for the convergence to Boltzmann equation. Start from a product measure, or a measure almost product up to the exclusion. Then the fluctuation field with some epsilon, so this is of the microscopic system, converges in the limit to a process, a stochastic process, which is governed by some SPD. I'm going to detail later on, where LT is just a linearized operator around Boltzmann equation. So this was conjectured a very long time ago already by Herbert Spohn, and so we provide a proof of this theorem for a time T star, essentially of the order of the convergence of the one of the Boltzmann equation. Let me emphasize that there has been already studies of the fluctuation in the case of stochastic model or stochastic type of collision by Fredoun, Rezahanlou, and much earlier for the Cax model by Cax, Logan, or Méléard. And the type of equation you end up with has exactly the same structure as this one. So the message here is if you start to look at correction to the Boltzmann equation, even if you start from a microscopic deterministic dynamics, you still get a stochastic equation which has qualitatively the same property as if you were starting from a stochastic process. So that's the physical somehow message of this theorem. So it's so let me say a few words on the stochastic equation. So there are two terms. I mean, one term is a linearized Boltzmann operator, and there is some noise. So of course, I mean, as such, the fluctuation field converges only in low to the limiting field, which is a distribution. But there are ways to interpret it. What is important, of course, and it's very much in the spirit of, I mean, the basic Ornstein-Uhlenbeck process, is on the one hand, there is some dissipative structure due to the linearized Boltzmann operator, a bit like Boltzmann equation. It dissipates, but the noise is there to feed some entropy or to restore at least partly the dissipation. Another thing important I mentioned earlier that this structure was already conjectured by Herbert Spohn, and at the time he already realized that the recollision in the system are important to recover the full structure of the covariance of the noise. So it requires a fine analysis of the microscopic system. An interesting example, and possibly the most basic, is to look at the equilibrium data. In this case, equilibrium initial data, sorry. In this case, I'm not going to start from a fancy measure. I'm just going to start from equilibrium, namely the distribution, initial distribution F0 is given by a Maxwellian, and otherwise the particles are uniformly distributed. Nevertheless, there is, in the system, there is some initial fluctuation because of this distribution, and some initial fluctuation which have this type of correlation in the limit epsilon goes to 0. And this initial correlation decay along the dynamics, and one can prove that they decay according to the the semi-group driven by the linearized Boltzmann operator. And this is the dissipation part. And at equilibrium, of course, the nice feature is that there, the noise exactly preserves the structure of the invariant measure. So the variance of the noise satisfy the fluctuation dissipation relation in order to compensate the dissipation. Okay, so that's more or less the take-home message from this theorem. Just want to mention, but it's currently a work in progress, that in the regime very close to equilibrium like this one, we should be able to establish the analogous theorem, but this time for long times, by which I mean times diverging with epsilon. Okay, so just a work in progress. Okay, let's, I've said that for this theorem, the correlations are important, and let's see what we can say about this, this correlation. Because when we computed the variance before in this example, we realized that we have to compute exactly the correct decay of correlation, otherwise the variance would not converge. So this means that to compute the correct decay, we have to understand what's going on the bad sets, the sets I've neglected earlier, because they would be irrelevant now. So the bad set, let me remind you, are the sets such that if I look at coordinates Z1, Z2, I want that they are such that if I take the dynamics for these just two coordinates along the backward flow, they're going to meet at some point. And what we can prove is that if I look at this 2-point correlation, which I'm going to call the cumulant of order 2, we can prove that this cumulant of order 2 decays, at least with respect to some norm, L1 norm, and the decay is exactly given by the volume of the bad sets. So that's on the bad sets where the correlation happen, but not too much. I mean, they are controlled, and they scale like epsilon d minus 1, okay? So I can do that for the 2-point correlation, but actually I'll need to look at more carefully at the other correlation, and the standard way to do that is to look at the cumulants. So just I just stated what is the third cumulant, but there's arbitrarily large number of cumulants, of course, which are going to record the dynamical correlation in this dynamics. Okay. And what we can show is that for higher order cumulants, so not only for the second cumulants, there is a decay, and the decay scales down with n minus 1. So let me remind you, when for the cumulant of order 2, the decay was related to the overlap between two tubes, and actually for the cumulant of order n, the decay is smaller and smaller because it's, again, it encodes n minus 1 dynamical constraint. So all these particles have to collide at some point. So that's what we can record from the cumulants. So we have this general theorem. So the epsilon in the previous the epsilon in the previous slide, or epsilon d minus 1 in the previous slide, is replaced by 1 over mu. In this slide, that's the only difference, because we are in the Boltzmann Grid limit, and we have this scaling which links the mean of the number of particles and the epsilon. So how do we prove that? I will briefly give some hints about that later on. The derivation of the decay of the cumulant is based on a dynamical cluster expansion. And of course, there we'll see that the interactions are much more complicated than at equilibrium. But the consequence of this theorem, before I say a few words about the proof, the consequence of the theorem is that it gives a precise control on the measure at any time, at least any time for which we know how to control the cumulants, which, by the way, is again, so there is some, I should have said that earlier, sorry, there is some time t star, roughly of order Lanford's time, such that we have a uniform control of all the cumulants for this small time, okay? And the important or the interesting feature of this cumulant is that if I want now to look at exponential moments of the empirical measure, if I want to look at this type of things, so h is a test function, I can expand it and I can relate it as a series in terms of the cumulant. So the series look bad because there is a factor mu epsilon n minus 1 here. It grows, of course, with the number of cumulants involved, but we have a good decay of the cumulants and the whole things compensate. Therefore, what we'll be able to say is that up to a certain time, which is non-trivial, a small time, but non-trivial, we have a full understanding or relatively good understanding of this measure. I will come back, sorry, of the exponential moment here. So I will come back to that later. Let me just give you, I mean, I mentioned the name, okay, sorry, that's important feature for later on. It is convenient to talk about the empirical measure at a given time, but these cumulants, since the whole thing will be based on a dynamical cluster expansion, we can actually consider function of the trajectories, of particle trajectories. So we can have several time at a go. I mean, it's not a problem. And we can have relatively good sampling of all the trajectories during a given time interval, 0 t star. Okay. So let me say just one word or a few words about the cumulant expansion. So it is a very well-known technique, and in particular for particles at equilibrium. So if imagine I have a gas of art sphere of radius epsilon at equilibrium, what should I do? The exclusion condition, namely that xi should be at distance at least epsilon from xj, I rewrite it as a 1 minus xi is at distance less than epsilon from xj. I close my eyes, I expand everything, and I get a decomposition in terms of graphs of some, let's say, interacting now structure or clusters. So this can be controlled by using combinatorial estimates, and at low density, one can control the Gibbs measure. At very low density, as we are considering now, everything converges really fine at equilibrium. The difference here is that we note at equilibrium, and so in this picture we have to add time now, and what we're going to do is perform the cluster expansion, but on the space of trajectories. So let's say that this is time 0, this is time t star, and one particle can go in straight line between these two times. Oops, sorry, just went too fast. Or a particle can touch each other and collide, or we may have more complicated collision. Nevertheless, now the object of interest will be these groups of particles. And for these groups of particles, we perform cluster expansion. Of course, they're no longer hard sphere. I mean, they are hard sphere at a single time, but they are trajectories now. So this requires to devise some geometric estimates in order to understand the correlation between the trajectories. And there, actually, you see that what is relevant even for one particle, is not the diameter of the sphere, it's the tube. The tube, it spans between time 0 and time t star, because we're playing now with interacting tubes. And okay, so we have dynamical graphs similar to those which can be found in a cluster expansion, and these dynamical graphs are related by the dynamical history, so there are collisions, there are overlaps, and all the structure of this dynamical graph is encoded through the cumulants. So that's how the control on the cumulants are obtained. Just very briefly, if we assume now we have the control on the cumulants, then we can deduce the convergence to the stochastic process, because we can look at the characteristic function. Of course, since everything is done kind of uniformly, whether the characteristic function is complex or not doesn't matter. We have uniform convergence, so we can really expand the characteristic function and show that what is relevant in this scaling of the fluctuation is a correlation, the correlation of order 2. And then it remains to identify the limit of the cumulants of order 2. So that's a bit more delicate, but it gives the exact covariance of the process. It turns out that one has to also handle the tightness of the process, but as I said earlier, with this strategy, we can have several times absolutely no problem, and we can also code or follow the fluctuation of the process. Okay, before, just to conclude, I want to explain the second consequence of this cluster expansion, which is another type of correction we want to understand from Boltzmann equation, is what's going on, or what is the probability if my system doesn't follow Boltzmann equation? What is the probability of observing an evolution which is far away, very different from Boltzmann equation, an atypical evolution? Let's call it phi. So phi is different from Boltzmann equation, and roughly speaking, what I want to say is that the probability of observing phi is tiny. It decays like exponential minus mu epsilon times some function, and I would like to understand what is this function, which will give me some understanding, of course, on the fluctuation of the process. So it turns out that for the CACS model, this has been done already, and even for much more complicated version than the CACS model by Fredun, Reza Hanlou, and one obtains some natural expression in the case of the stochastic dynamics for the large deviation function f hat. I just wrote it below, and this one was, when you add the position, this one was conjectured by Freddy Boucher, but okay, you don't really need to, it's just to say that there is some explicit expression up to a variational problem of what is the probability of observing some atypical function phi. And the question is, okay, does this extend to the deterministic microscopic dynamics? And the answer is yes, at least in some regime. So again, for the T star for which we can control the cumulants, we can find a large deviation function, but it's valid, of course, not for all phi. It's only valid for a restricted set of phi, which is actually close to the solution of Boltzmann equation. I mean, I can't say if we are going too far, that would require too complicated technical control on the system. But if I look at a different solution from the Boltzmann equation, but not that far away from it, then we can prove that there is this exponential decay, and that this exponential decay, okay, holds on a restricted set, and on a set slightly smaller, we can actually prove that the functional we found for the deterministic microscopic dynamics matches exactly the one found for the CACS model. So there is actually, even in the finest structure of the large deviation, the heuristic we can get from the stochastic dynamics of the stochastic picture matches the one we find for the deterministic system. Okay, so. What are the difficulties for this theorem? For those of you who've been probabilists, you know that the best way to understand or to prove large deviation is to tilt, or you start from a stochastic dynamics and you tilt the dynamics in the way which is going to produce the deviation you would like to observe. Here we have a bit of a problem because the randomness is only at the initial time. And we don't have any stochastic dynamics, and we don't know how to tilt the measure initially to create the deviation we want. There is no direct access to the dynamics. So we go around this problem by looking once again at the exponential and using our refined control on the cumulants. We control the convergence of this series in order to really understand the Laplace transform, and then the Laplace transform is related to the large deviation function. Just one word before I conclude, because I think it's almost time. The identification of the large deviation function from the microscopic system to the one which follows from the stochastic dynamics is done by proving that somehow this Laplace transform obeys a kind of Hamilton-Jacobi equation. So we have for a restricted set of test function, we can prove that this Laplace transform converges to some functional I, which depends on t and h. And this functional has a limit given by a Hamilton-Jacobi equation. And by playing with this Hamilton-Jacobi equation, we can identify it with the stochastic model, which has the same structure, actually. So that's all I'm going to say, because time is up. So just to summarize, what is maybe the take-home message is that even so we start from a microscopic dynamics which is deterministic. Turns out that as any type of measurement or reasonable physical measurement you want to do on the system, namely by testing a macroscopic structure like empirical measure, is still going to be recorded by the stochastic structure you can guess from the usual phenomenological approach, which says that particles are almost independent and you have chaos property, and essentially you have as if you have an underlying stochastic process. So that's the message, and this message remains valid up to exponentially small deviation as the large deviation. It means that essentially all the reversibility is stored in directions which are completely orthogonal to the microscopic observable we are interested in. And of course, there are many problems, and I have to stop, but one of the big issues is trying to understand the long-time dynamics now out of equilibrium. Thank you very much.
Thank you, Thierry. Are there some questions in the room? Yeah.
So, you mentioned that using the cluster expansion, there's hope to control the fluctuations over long times.
No, I mentioned that with the cluster expansion as such, we can control up to time t star. To control over a long time, I think you need different tools.
But didn't you mention that there was work in progress to
Oh yeah, but
the...
we don't use exactly. Okay, sorry. So this, sorry. There we don't use the cluster expansion, or we don't use it as such. We use it locally, close to equilibrium, to evaluate specific events. But otherwise, somehow it's. I mean. It's the cluster, you see the validity of the cluster expansion, even for hard sphere particle at equilibrium, is limited to the density of the gas. And there, the density of the gas, if we see it as a dynamical gas, increases with time. So there'll be, I mean, I don't know whether the T star is the right one, but there'll be one time where it collapses, and maybe you're a bit better with combinatorings, but it's going to collapse a bit later.
Another question?
Do you have estimates on the typical size of clusters of correlated particles? I mean, those who are correlated by recollisions.
Okay, so no, what I mean, the estimates we have are sorry. About the decay, and this decay tells you, sorry, where is it? So about this decay, and this decay tells you that essentially to launch a cluster, you really have to have the tube in certain geometric position. So that says essentially the probability of such cluster is proportional to or is related to this type of decay. After we don't really use it as such because for us, I mean, it's important that they don't occur that often. Okay.
John Michele?
You said that the only cumulant of the fluctuation field that was relevant was the second one.
Yes.
Is this another way of saying that the fluctuation field is Gaussian?
Yes, that's exactly it. Yes, the fluctuation field is Gaussian. It's just very much in the spirit of some Einstein-Uhlenbeck process where the noise. Sorry, I want to say it here. So where is it? It's here. So the whole thing is actually linear here, and the noise is wide in space and time, and it has some correlation in velocity because it is. I mean, it has to preserve the momentum and the energy, but otherwise it produces Gaussian fluctuation. Yes.
Another question? Yes.
There was a... okay.
You said that the time T star that appears in your theorems are basically the same length for time, so there are very few collisions.
Exactly, yes.
On the other hand, you said that recollisions are very important in order to obtain this theorem.
Yes.
But, and you say you go back in time, so that means you go before time zero.
No, okay, when I say, oh, sorry, maybe what I said before, which of these bad sets are essentially two particles when if you are at a time t, whether they've seen each other up to time zero, not beyond time zero. So, okay, it's the condition was very loose, but okay, I don't want to go before time zero, just whether they've seen each other up to time zero. Because at time zero, I know that they are roughly independent.
Okay, then the other question is, you didn't write down what is the variance or the covariance of the field. There is some Green-Kubo formula that
yeah, actually not even is the one you think. So it's really the one at equilibrium. It's the one which compensates the dissipation of the linearized operator. So there's not more than that.
Okay, there was another question up there.
There was a regularity assumption that F0 is smooth, and I was wondering if either on the law of large number or on the fluctuation, if there is a regime of regularity where, say, the Boltzmann equation would still be meaningful, but on the microscopic system would want to do something else?
No, because the way we do it is ultimately we want to think of it as a coupling with a Boltzmann system, and we are in a regime where we need also a lot of control on the Boltzmann equation. So I mean it's not clear to see how they would depart. I mean the assumption on F0 are also are very useful for us to do a kind of precise coupling at a microscopic level. We don't want that ultimately. So we have particles of size epsilon. And we want this particle to shrink up to 0. And we want just to make sure that all these possible shifts of order epsilon are not causing problems. So we really need, with this respect, some strong regularity. And I don't know to which extent we can get rid of it, whether it's purely technical, but it seems useful at least. So I'm not sure I can comment more.
Okay, so if there are no more questions, I think we can thank Thierry again. And we meet in 25 minutes. Yeah?